Hi everyone. So in the last lecture we have seen how to create a circuit for frequency division by 2. Okay, so we have already seen that a T flip-flop, if you have, then T flip-flop will divide the frequency by 2. Okay, now let's see this question. Assume you have a clock signal of frequency f hertz. Okay, so basically it means that f oscillations per second. How to generate another clock of frequency f by 2 power k hertz. Okay, so basically we want to divide the frequency by some power of 2. For example, maybe if you, okay, we have already seen that if you have a T flip-flop, this T flip-flop you have, okay, you connect this T with 1. Now what will happen? The output will toggle, because whenever T is equal to 1, then the output will toggle. In every clock pulse, the output will toggle. This is your clock, okay, and this is your output. You know that if this clock has f hertz frequency, then this output will have f by 2 hertz frequency. Okay, so this we have already seen, this we have seen. Okay, now what we want a circuit which, okay, to which you give f hertz frequency clock, okay, and the output must be f by 2 power k. So basically here we are dividing by 2, and now what we want to do, we want to divide by 2 power k. Okay, so where k can be some integers. Okay, so we want to divide the frequency by some power of 2. Okay, so how to do that? What we can do, okay, if you want to divide by 2 power, for example, let us assume that you want to get a frequency of f by 2 power 2, basically f by 4. Then what to do? The idea is very simple. You already know that this is a T flip-flop. Okay, this is your T flip-flop. You already know that this is your clock. Okay, let's assume this clock has f. This is your frequency, this is f hertz, this is the frequency. Okay, now you know that this output will have f by 2 hertz frequency. Okay, now what you do, the idea is very simple. Now just, okay, just apply this, okay, to another T flip-flop. Take another T flip-flop, and what you do, in this T flip-flop, what you do, the clock, so basically the clock must be this. Okay, so basically what you do, the idea is very simple. This is your f hertz clock. Okay, this is a clock which has frequency f hertz. Okay, so I can say this is your clock. Okay, clock. Now, so this T flip-flop, this, the output of this T flip-flop will have frequency f by 2. So basically this output waveform, this has frequency f by 2. Now what you do, another, okay, this frequency, this clock, sorry, this pulse, okay, this pulse you pass through another T flip-flop. So what you will get? So basically this output of this flip-flop we are giving as a clock to the next flip-flop. Now what will happen? So basically I can say, now this is the clock, okay, and now this output will have frequency this divided by 2, f by 2 divided by 2, so that means f by 4. Okay, so this now has frequency f by 4 hertz. So like this you can do. Okay, now for example, if you want 2 power, okay, so you can notice, if you want 2 power k, if you want to divide the frequency by 2 power k, then what you can do, in the same manner, in this similar manner, what you can do, you can connect k flip-flops. Okay, so I can say that, for example, I can say that if you have this is your T flip-flop, this is another T flip-flop, this is another T flip-flop, this is another T flip-flop. Okay, now you can notice this is the clock. So this is the clock, let me call it ck. Ck means clock. Okay, this is your T flip-flop, this is T flip-flop, T flip-flop, T flip-flop. Okay, again you can notice this is clock, this is clock, okay, and this is also clock. Now, okay, so this is the q in, this is the q output, q output, q output. Okay, now the idea is this. So this clock, the clock that, okay, this is the clock signal that you are applying. Okay, so this clock signal has f hertz frequency. Okay, now this output will have, definitely what will happen, this output will definitely have f by 2 hertz frequency. Okay, what you do, now this output you give as a clock to the next flip-flop. Okay, so this output, the output of this flip-flop will work as the clock to the next flip-flop. Now you can notice, basically now this clock has, okay, this clock signal, this has f by 2 hertz frequency, then this output will have f by 4 hertz frequency. Okay, now this output you give as a input to the next flip-flop. Okay, I can say this output you give as the clock to the next flip-flop. Okay, so this has f by 4 hertz frequency, so the output of this flip-flop will be f by 8 hertz frequency. Okay, because you already know that. Okay, so let's assume this is connected to 1, this is also connected to 1. Okay, and this is also connected to 1, because you already know that this is the divide by 2 circuit. This circuit will divide the frequency by 2. Okay, so if the input frequency is f by 4, then the output frequency will be f by 8. Now again you can notice that this output of this flip-flop you can give as clock to the next flip-flop. Okay, now this clock has frequency f by 8 hertz. Okay, so the output will have frequency. Okay, I can say that this output will have frequency f by 16 hertz. So this is the idea. Okay, so you can notice, if you want to divide by 2 power k, then what you can do in the same manner. Okay, so here you can notice that, okay, this is, remember, this is a asynchronous circuit. Why this is asynchronous sequential circuit? Or I can say this is asynchronous counter. Why this is asynchronous counter? Because you can notice that the output of this flip flop is working as clock to the next flip flop. The output of this flip flop is working as clock to the next flip flop. So you can notice the same clock is not applicable to the all flip flop. I can say all these flip flop, they are not operated by the same clock. You can notice this is the system clock. So the system clock is operating this first flip flop. Okay, and output of this first flip flop is operating the second flip flop, and the second output of the second flip flop is working as clock for the third flip flop, and so on. So this is a asynchronous counter, and you can very easily see that this circuit. Okay, just look at this circuit, just look at this circuit. This circuit will divide the frequency by 2 power 4. Okay, so if your input frequency is f hertz, then the output frequency will be f by 16 hertz. Okay, so you have divided the frequency by 2 power 4. Okay, so this is the idea. So if you want to divide the frequency by, let's assume this is the circuit. Okay, now this is the clock, this is the clock signal, and let's assume this clock signal has f hertz frequency. And if you want to divide the frequency by 2 power k, then what you can do? Then very simple, k t flip flop you can connect. Okay, so how many t flip flop? So I can say that total k t flip flop. Okay, k t flip flop you can connect. Okay, and you can connect like this. Okay, so the output of one flip flop will be acting as clock for the next flip flop. Okay, and this will work. Okay, so like this. Okay, so this is the basic idea, I can say. So this is the basic idea. Okay, so like this you can do the frequency division by 2 power k. Okay, I hope this point is clear. Now let's also see the timing diagram, basically the waveform diagram we will also see. So let's assume that we have this circuit. Okay, so there are two T flip flop, and you can notice that the output of this flip flop, output of the first flip flop is acting as clock for the next flip flop. So we have already seen that this circuit, if you note, if this circuit will actually divide the frequency by 4. Okay, so I can say this circuit, because we have two flip flop. Okay, and they are connected like this, so the output frequency will be f by 2 power 2. So I can say output frequency will be f by 4. Okay, now let's see the timing diagram also. Let's see. Okay, so let's assume this is the clock signal. Okay, so this is the clock waveform. Okay, now I can say, so what will be q0? So let's assume this is the output q0, and let's assume this is the output q1. So what will be the waveform for q0, and what will be the waveform for q1? Okay, so let's check it out. So you can see here that both these T flip-flop, these are basically positive edge triggered flip-flop. So when the clock is going from 0 to 1, when the clock is going, okay, when the clock is making this positive edge transition, okay, I can say, okay, see, when the clock is having this rising edge, then you can notice that, okay, because remember, only this T flip-flop, only this flip-flop is basically, I can say, is affected by this clock. Okay, so this clock is only applicable to this flip flop. Okay, so I can say when this clock is going from, okay, I can say finally when this clock is going from 0 to 1, then this flip flop, this q0 will toggle. Okay, because this t is connected to 1. So I can say that when this clock is going from 0 to 1, then this q0 will toggle. Okay, so let's assume that initially q0 comma q1, let's assume initially both are 0 0. Let's assume. Okay, now I am saying that when this clock will go from 0 to 1, this clock, okay, because this clock is basically applying to this first flip flop. Okay, so I can say when this clock will go from 0 to 1, and because this t input is 1, so I can say whenever, okay, with every clock pulse, with every rising edge, this q0 will toggle. Okay, so I can say that initially your q0 is 0, then with every rising edge, what will happen? With every rising edge, this q0 will toggle. Okay, because you can notice this for the first flip flop, you can notice the clock, we have applied the clock. Okay, so I can say, so this input clock, this is the input clock, you can note this is the input clock. This input clock is applicable, is operating this first flip flop. Okay, and the t input is 1. So I can say with every clock pulse, I can say with every rising is the output of this flip flop, this q0 will toggle. Okay, so this is how we will get, so this type of waveform we will get for q0. Okay, now you can notice that the output of this first flip flop that is working as clock for the second flip flop. So what I can say, again, this is positive edge triggered. So what I can say, I can say when q0, when this is going, when this q0 is going from 0 to 1, then this flip flop will toggle. Okay, so when this q0 is going from, okay, so I can write it here. When q0, okay, when q0 is going like this, when q0 is going like this, okay, then I can say this q1 will toggle. Okay, then this q1 will toggle. Okay, so this is the simple point, because you can notice for this flip flop the clock is this output. So this q0 output is the clock for this flip flop. So I can say when this q0 will go from 0 to 1, because you can notice this is a positive edge triggered flip flop. So when this q0 will go from 0 to 1, then I can say this q0 will toggle. Okay, so you can notice when this q0 is going from 0 to 1, here you can notice this q0 is going from 0 to 1, and here also q0 is going from 0 to 1, here also q0 is going from 0 to 1. So you can notice here what will happen, the q1 will toggle. Okay, and q1 will toggle then again. Okay, then q1 will toggle here, then q1 will toggle here. Okay, and so on. Okay, and so on. So for example, let's assume that you have this type of scenario. Okay, then here I can, okay, I can extend this diagram also. So here what we can have, so like this, let me just extend this. Okay, so this q0 will toggle whenever this clock will make positive edge. So with every rising edge of this clock, okay, the q0 will toggle. And similarly with every rising edge of this q0, with every rising edge of this q0, this q1 will toggle. Okay, so this q1 will toggle with every rising edge of this q0. Okay, so like this you will get. Now you can very easily notice here, okay, that the frequency of q1, if you notice, okay, so the frequency of this q1, frequency of this output. So what is the frequency of q1? You can notice this is the time period of q1. Okay, so let me just write it here. So you can notice from one rising edge to another rising edge. So you can notice this is the time period, this is the time period of q1, this is the time period of q1. Okay, and what is the time period of q0? This is the time period of q0. Okay, so I can say that this is a time period of q0. Okay, and you can notice time period of q0, that is basically double of a time period of clock. Or I can say the frequency of q0 is basically half of frequency of clock. Because you can notice in, okay, in this time period, okay, you can very easily notice that in this time period, just look at here. Okay, in this time period, in this time period you can notice, okay, there are two time periods of the clock. Okay, so in one time period of q0 there are two time period of the clock. Okay, and similarly I can say in one time period of q1, this is the one time period of q1, in one time period of q1 I can say there are four time periods of, okay, there are four time periods of clock. So I can say that the frequency of q1, that is basically, this is f by 4. I can say the frequency of q1 is, okay, 1 by 4 of frequency of the clock. Okay, so this is the idea. I can say that the this circuit, you can notice this circuit will divide the frequency by 4. Okay, so this is the idea. So from this we can notice that this circuit will divide the clock frequency by 4. So actually this circuit, we can say that this is basically divide by 4 circuit. I can say this is divide by 4 counter. Now see, divide by 4 frequency division is happening, that you can very easily see that the clock frequency we are dividing by 4. So this is divided by 4 counter. But why we call it counter? Like what it is counting, what is the sequence of states it is going through? Because the definition of counter says that a counter is basically a sequential circuit which goes through a sequence of states. So here you can notice frequency division is definitely happening. You have already seen, because you can notice the frequency division we are doing. But why we call it counter? What is the sequence of states this circuit will go through? Okay, so let's see that. So clearly there is some division, frequency division going on, but how do we interpret this as counting? Okay, so let's see that. So this is your circuit. Now in this circuit, let's assume this is the clock. Then what will be the output waveform of Q0? So let's assume that initially Q0 comma Q1 both are 0 0. Let's assume. Now here one thing you should notice, that whenever this clock will go from 0 to 1, because this is a positive edge triggered T flip flop, this is also positive edge triggered T flip flop. So what it means? It means that whenever this clock will go, I can say that this clock, okay, if this clock goes from 0 to 1, okay, then I can say then this q0 will toggle. Okay, so then definitely I can say that this q0 will toggle, because you can notice this T flip-flop is operated by this clock. Okay, so I can say with every clock pulse, with every rising edge of this clock, I can say the Q0 will toggle. And similarly, you can notice that because the output of this flip-flop, this Q0 is acting as clock for the second flip-flop. So I can say that with every clock pulse, okay, I can say with every rising edge of this Q0, I can say that Q1 will toggle. So I can similarly I can say that if Q0 goes from 0 to 1, means with rising edge of Q0, I can say then I can say Q1 will toggle. Okay, so this is the simple idea. Now let's apply this. So let's assume initially q0 comma q1 both are 0 0. Let's assume now what will happen with every rising edge. This is the rising edge, you can notice these are the rising edge of the clock. Okay, and the clock is only applying to the first flip flop q0. So with every rising edge of the clock, I can say that q0 will toggle. Okay, so you can notice that q0 will toggle with every rising edge. Okay, so like this. So this is the output waveform of q0. Okay, this will be the output waveform for the q0. Okay, you can just write it like this. With every rising edge of the clock, q0 will toggle, because remember the input t is connected to 1. Okay, so whenever t is equal to 1, then with every clock pulse the I can say the output will toggle. And you can also see that this q1, what about this q1? For this q1, you can notice the output of this flip-flop, means this q0 is acting as clock for this flip-flop. So I can say whenever this q0 will go from 0 to 1, then q1 will toggle. Okay, so you can notice the q0 is going from 0 to 1 here. Okay, so this is the rising edge of the q0. Okay, these are the rising edges of the q0. So here what will happen, here q1 will toggle. Okay, so q1 will toggle here. Okay, whenever q0 will go from 0 to 1, then q1 will toggle. Okay, so q1 will toggle here, then again q1 will toggle. You can notice, okay, q1 will toggle here, then again q1 will toggle here, and then again q1 will toggle here, and so on. Okay, so like this. Now let's see here what is happening. You can notice that initially q0 comma q1 both are 0 0. Okay, so you can very easily see that initially both are actually 0 0. Now what will happen? Now after this, okay, initially both are 0 0, you can very easily see. Okay, so I can say that both are 0 0. Now after one clock pulse, after one clock pulse, you can notice that here, okay, initially both are 0 0. Then the next, what is the next? Next is both are 1 1. Okay, so you can very easily see after one clock pulse, now I can say that both are 1 1. Okay, so this is 1, this is 1. Okay, so from 0 0 basically they are going to 1 1. Okay, and what is the next state? From 1 1 where they are going. Okay, so you can very easily see. So from this 1 1 they are going to 1 0, and then they are going to 0 1. Okay, so let's assume that here in this circuit, let's assume this is the LSB, let's assume this is least significant bit, and let's assume this is a most significant bit. Means Q0 is the least significant and Q1 is the most significant. Then you can very easily see that from this state, I can say that from this state. Okay, so I am writing, remember I am writing Q1 Q0, because remember this is LSB, Q0 is LSB, and I'm assuming that okay, this Q1 is MSB. Let's assume that this is LSB, okay, and this is MSB. Then in this case, you can very easily notice that from state 0 0 we are going to state 1 1, and then from state 1 1, okay, now from 0 0 we are going to state 1 1, and from state 1 1 we are going to 1 0, because Q1 is MSB, Q0 is LSB. So I can say then we are going to 1 0. Okay, and then from this state we are going to 0 1, and then from 0 1 we are going to 0 0. Okay, so from 0 1 the next state is 0 0. Okay, so like this you can notice, and then from 0 0 again we are going to 1 1. So from 0 0 again we are going to 1 1, from 1 1 again we are going to 1 0, from 1 0 again we are going to 0 1, and then again we are going to 0 0. So you can notice this is the sequence, this is the state sequence through which counter is going on. Okay, so you can notice this circuit is a counter. Why? Because this circuit will go through this sequence of states. If you start in this state, let's assume this is your initial state 0 0, then the next state will be 1 1, next state will be 1 0, next state will be 0 1, next state will be 0 0. Okay, so basically you can very easily notice that basically from 0 you are going to 3, from 3 you are going to 2, from 2 you are going to 1, and then from 1 you are going to 0. So basically this is a I can say down counter. This is a binary counter, because you can notice we are okay. We have already seen that this is a binary counter, but this is a binary down counter. Okay, so you can notice this circuit. I can say this circuit. What I can say for this circuit, this is basically binary counter, but this is binary count down counter. Okay, this is count down counter. Okay, and this is the sequence of states through which this counter will go. Okay, so this is the sequence of states. So there are total four unique states here. So I can say, because you have total four unique states, this counter is going through four unique states. So I can say that this counter is basically, I can say that this is a modulo 4 counter. Okay, so finally I can say that this is a binary countdown counter. I can also say that this is modulo 4 counter. Okay, I can say this is modulo 4 counter, because modulo 4 counter, why? Because there are four unique states this counter goes through. Okay, so this is the whole idea. Now, so that is the reason we call it counter. So you can notice this circuit, if you notice, this is a frequency divider. We call it divide by 4 counter. Okay, another name you already know, this is divide by 4 counter. Okay, so this is divide by 4 counter. Another name is mode 4 counter. Another name is binary countdown counter. Okay, so because this is counting in the reverse direction. Okay, you are going from 3 to 2, 2 to 1, okay, 1 to 0, like this. So this is the binary countdown counter. This is okay. We can also say this is mode 4 counter, because there are four unique states. Okay, the counter is going through four unique states. So that is the reason I can say this is a mode 4 counter, modulo 4 counter. Okay, and I can also say that this is a divide by 4 counter. Okay, so these are different properties of this counter. Okay, now one more interesting thing we need to see here. What is that? You can notice that you can notice in practical, in real life, every flip flop has a propagation delay. Okay, so here you can notice in this diagram, actually we are assuming that there is no propagation delay. In this diagram we are assuming that this flip flop, okay, this flip flop, they don't have any propagation delay. But in real life, what happens? In actually, okay, they have some propagation delay. Now let's see. If we assume, okay, actually it happens, because in real life every physical circuit, every hardware has some propagation delay. Okay, so you can notice that this flip flop also have some propagation delay. In that case, let's do the analysis. Okay, so in real, you can notice that every flip-flop has some propagation delay. So let's assume that our flip-flop, we are using T flip-flop. Let's assume that propagation delay is a TPD. Okay, so this is our circuit, and let's assume that propagation delay of this circuit is this flip-flop is TPD, and propagation delay of this flip-flop is also TPD. Okay, now let's see in this situation what will be the waveform. So you can notice, let's assume this is the clock. Okay, and you already know that when this clock will go from 0 to 1, when this clock is making the rising edge, then this q0 will toggle, and the output, basically this q0 is the clock for the next flip flop. So I can say when this q0 will go from 0 to 1, then q1 will toggle. Now here, what is the waveform for q0? So let's assume initially q0 comma q1 both are 0 0. Let's assume, okay, so both are 0 0. Now what will happen? Okay, so now you can notice with every rising edge of the clock, the q0 will toggle. So here q0 is toggling. Okay, with every rising edge, q0 will toggle. So this is your q0. Okay, because you can notice with every rising edge the q0 will actually toggle. Okay, now what will happen to q1? Q1 will toggle with every rising edge of q0. Okay, whenever q0 is going from 0 to 1, because remember, these flip flop, these are positive edge triggered flip flop. Okay, and you can notice for this flip flop the clock is basically this q0. Okay, so I can say when q0 is going from 0 to 1, then in that case this flip flop, basically this output q1 will toggle. Okay, because you can notice that t input is 1. Whenever t input is 1, then with every clock pulse, with every rising edge, this output will toggle. Okay, so here what will happen? So with every rising edge of q0, with every rising edge of q0, what will happen here? This q1 will actually toggle. But remember here one more thing. Actually we are assuming that we are taking this case that every flip flop has propagation delay. So actually this waveform we have to change. Actually what will happen here? Because every okay, so okay, so let me just create it. Because remember, you can notice that every flip-flop has propagation delay, because in real life every hardware, every digital circuit has propagation delay. So let's assume that in real life the flip-flop also has propagation delay. So let's assume the propagation delay is TPD. Now what will happen? See, with every rising edge of the clock, q0 will toggle. Okay, so this q0, initially the q0 is 0. Now what will happen? You can notice that now this will happen. See that when this rising is, when this clock is going from 0 to 1, then q0 will toggle. Q0 will definitely toggle, but after some, like, there is a propagation delay. There is a propagation delay. So q0 will toggle, but there is a propagation delay. Okay, so you can notice this is the propagation delay. I can say this is the propagation delay. Okay, so here I can say this is the propagation delay. With every rising edge, this is the rising edge of the clock. Again Q0 will toggle, but there is a propagation delay. There is a propagation delay, so like this will happen. Again here there is a propagation delay, so like this it will happen. And here again there is a propagation delay, so like this it will happen. So this is the output waveform of Q0. Now whenever Q0 is going from 0 to 1, whenever Q0 is going from 0 to 1, then Q1 will toggle. So now you can notice that Q1 will toggle when Q0 is going from 0 to 1. Okay, when Q0. So here you can notice when Q0 will go from 0 to 1. So this Q0 you can notice. Okay, so when this Q0 is going from 0 to 1, then this Q1 will toggle. Okay, so you can notice here. Okay, now at this moment you can notice, at this moment Q0 is going from 0 to 1. So now at this moment Q1 should toggle, but there is a propagation delay. So because this flip-flop also has propagation delay TPD, so what will happen? This Q1 will toggle, but okay, it will toggle after the propagation delay. Okay, so this is again the propagation delay. So again you can notice here also this Q1 will toggle, but this is the propagation delay. So like this. Okay, so like this it will happen. Okay, so very easy. So now you can notice the sequence. Okay, here one thing you should notice. What is that? Okay, just notice here one thing you should notice here. Okay, first of all, the first thing is every flip-flop in real life, every flip-flop has propagation delay. So what it means? Propagation delay means when you apply the input, when you change the input, then output will change, but after some time. Okay, so this is the point. Okay, so you are changing the input, but output will change after some time. Okay, so this is the propagation delay. Now you can notice here clock is going from 0 to 1. So you are changing the input, but the output will change after some time. This is the propagation delay. Similarly, here you can notice the Q0 is going from 0 to 1. So the output will change. This Q1 will change, but after some time. Okay, so after the propagation delay. Okay, so this is the point. Now here one thing you can notice, what is that? That here there is a okay, so just notice here what is happening here. See here initially they both are in this state 0 0. Okay, so initially they are in this state 0 0. Now what will happen? Okay, you can notice for a moment, just notice for a moment what is happening. Okay, yeah, at this moment, okay, during this duration, just look at this moment. Okay, just look at this. Okay, just look at this moment. You can notice what I'm saying. Okay, just focus on this. So here you focus. So you can notice at this time, okay, during this period, for a very small moment, I can say for a very small moment, you can notice what is happening here. You can notice that Q0 is 1 and Q1 is 0. Okay, so I can say this is your Q1 Q0. So okay, from here for a moment, I can say for a moment what is happening, for a very small moment what is happening, that I can say that Q1 is 0. For a very small moment Q1 is 0. Okay, but Q0 is 1. Okay, so you can notice for this very small moment, you notice that Q0 is 1 but Q1 is 0. Okay, so Q0 is 1. Okay, but Q0 what I'm saying is Q1 is 0 and Q0 is 1. Q1 is 0 and Q0 is 1. Okay, and immediately after what will happen? Okay, and then afterwards you can notice both are 1 1. Okay, so actually both are 1 1, but for a moment I can say this is called transient state. This is called transient state. What it means? This is momentarily, basically this is a moment, this is a glitch. I can say this is a glitch. Okay, just let's call it glitch, because you can notice. Okay, I hope this point is clear to everyone, because you can notice that from this 0 0 actually we are going to state 1 1, but there is a glitch, there is a transient state. Okay, and this transient state is due to, okay, this is because of this propagation delay. So because of propagation delay of I can say of flip flop, because of propagation delay of flip flops, propagation delay. Okay, because of propagation delay of flip flops, okay, we get transient states. We get transient states. Transient states, basically these are just some glitches. Basically we get some glitches. Okay, so you can notice here in this, because of propagation delay, this, okay, just notice this moment, you notice in this moment you can see that Q0 is 1 and Q1 is 0. Okay, so you can notice Q0 is 1 and Q1 is 0. Now immediately after what will happen? Now you can notice that both are 1 1. Okay, now again you can notice, so both are 1 1. Now what will happen here? Just notice here. Okay, so now again they are, okay, this is 0 1, But you can notice for a moment what is happening. Okay, just look at again, look at this moment, just look at this moment. In this moment you can notice q0 is 1. Okay, and q0 is 1 and q1 is also 1. Okay, this moment you notice. Okay, anyway, so okay, then what is happening, then this q1 is 1 and q0 is 0. Okay, so from here this, okay, so this here you will go. Okay, now again what will happen here. Okay, again you notice here, again for a moment what will happen, for a moment what is happening, just notice here. So this is a, I can say, okay, so this is 0 1. Now for a moment what will happen, this is 0 1. Just look at this moment. Okay, just focus on this moment. So let me write it here. Okay, so just focus on this part, this duration of this. Okay, so here you notice, here what is happening, here you can notice that q0 is 1 and q1 is also 1. Okay, so here actually for a moment both are 1 1, both are 1 1 for a moment. Okay, for a moment both are 1 1, and then you can notice then q0 is 0. Okay, so q0 is 1 and then q1 is 0. Okay, so like this it is happening, and then you can notice both are 0 0. Okay, so here from here both are 0 0. Okay, so this is the idea. So again this is a transient state. Again I can say that this is a transient state. Okay, so finally I can say that in this this is your asynchronous. Why this is happening, because this is asynchronous. You can notice this clock is applying to this flip flop, and the output of this flip flop will control this flip flop. Okay, so you can notice this clock is controlling this, and this q0 is controlling q1. Okay, so that is the reason I can say that and there is a propagation delay also. Okay, we know there is a propagation delay of flip flop. Okay, so that is the reason I can say that here what is happening, these glitches we are getting. Okay, so I can say from state 0 0 actually you should go to state q 1 1. Okay, from state 0 0, this is your state 0 0. From this state you should go to 1 1. Okay, but for a moment, for a very small moment, for a very small moment, this state will come for a very small moment. So that is the reason I am putting it in dot. Okay, because for a very small moment this state will come. So this is just a glitch. Okay, so you are going from 0 0 to 1 1, but there is a glitch here. Similarly from 1 1 you will go to 1 0. From 1 0, from 1 0 you should go to here, you should go here, but there is a glitch, there is a glitch 1 1. Okay, and then from 0 1 you will go to 0 0. Okay, so this is the idea. So I hope this point is clear to everyone. So because of propagation delays of flip flop, I can say we get transient states in asynchronous, in asynchronous counter. In asynchronous counter, this is what happens. Okay, now actually you can also understand this by this logic, because you have what you have. So you have basically two t flip flop. You can notice this is your q0, and this is working as clock for the next flip flop. This is your q1, this is your t. Okay, and this is the clock. Now you can very easily notice that when this clock is going, basically when, okay, if the when, I can say when this clock, notice when this clock is going from 0 to 1. Okay, then what happens, then you can notice then that q0 toggles. Okay, this you already know. Okay, similarly when q0 is going from 0 to 1, then q1 toggles. This also you know. Okay, so now you can actually, and there is a propagation delay also, because you can notice there is a small propagation delay of every flip flop. So now here actually this you can do, you can do like this. Okay, so this is q1, this is q0. So we are assuming that this is least significant bit and this is most significant bit. Then what will happen, so here after one clock pulse, so let's assume initially you have 0 0, let's assume. Okay, now after one clock pulse what will happen, after one clock pulse. Okay, so I can say this is your, okay, this is your first clock pulse. Okay, I can say this is your initial state. Now after one clock pulse, this is your clock, I can say. Okay, so after one clock pulse what will happen, after one rising is, definitely after one clock pulse this will go from 0 to 1. Okay, because you already know that with every clock pulse this q0 will toggle, this q0 will go from 0 to 1 with every clock pulse. Okay, in the next clock pulse this will go to 0, in the next clock pulse this will go to 1, in the next clock pulse this will go to 0, in the next clock pulse this will go to 1. Okay, so you can notice with every clock pulse this q0 will definitely toggle. Okay, now because with every rising edge of the clock this q0 will toggle. Now you can notice when the q1 will toggle, q1 will toggle when q0 is going from 0 to 1. Okay, so you can notice here q0 is going from 0 to 1. Okay, just notice here. So in this situation q1 will toggle. Okay, q1 will toggle here when q0 is going from 0 to 1, then q1 will toggle. Okay, similarly when this q0 is going from 0 to 1, then q1 will toggle. So here q1 will not toggle, here q1 will toggle. Okay, and here q1 will not toggle, but here q1 will toggle. Okay, when q0 is going from 0 to 1, then q1 will toggle. Okay, so like this also you can analyze. Now you can very easily notice that, okay, this is q1 q0. Okay, so from 0 0 you are going to 1 1, and from 1 1 you are going to 1 0, and from 1 0 you are going to 0 1, and from 0 1 you are going to 0 0. Okay, so this is the point. Now the same, so here we are assuming, okay, when you are doing this analysis, then we are assuming that there is no propagation delay. But when there is a propagation delay, then what will happen? Now notice what will happen. Okay, so you can very easily notice that this will happen when there is a propagation delay q1 q0. Okay, initially you are in this state. Okay, from this state actually you will go to 1 1, but you can notice this change will not happen simultaneously. Okay, from this state you will go to 1 1, you will go to 1 1, but this change, okay, because both are changing, this also changing, this also changing, this change will not happen, okay, simultaneously. For a moment, for a very small moment, for a very small moment, what will happen? First this will change. Okay, so first this will change because this is q0. First this will change. Okay, okay, for a very small moment what will happen? This will change. Okay, and at that time this will be as it is. Okay, so you can notice for a very small moment this will change. Okay, now after that it will change. So you can notice for a very small moment q0 will change. Okay, and then when q0 is changing, then q1 will change. Okay, so because you can notice here, okay, first q0 will change, and when q0 will change, then q1 will change. Okay, so very easily you can notice that this clock, okay, okay, clock, okay, every rising edge of the clock, what it will do, it will change q0. Okay, so you can notice change in clock, I can say change in clock. Okay, basically, okay, change in clock from 0 to 1, of course. So change in clock, that immediately implies change in q0, I can say. Okay, so that implies change in q0. So first q0 will change. Okay, and once q0 will change, then q1 will change. Okay, so I can say here, then q1 will change. So you can notice first q0 will change for a moment, and then q1 will change. So here you can notice from 0 0 you will go to 1 1, but for a moment what will happen? First q0 will change, and then q1 will change. So first this q0 is changing, and then you can notice then q1 is changing. So you can notice this state, this is a transient state, and this is a momentarily. Okay, for a very small moment this will happen. Now again here what will happen? Again here only very simple, you will go to which state? You will go to 1 0. So only this is changing. So you can notice this is changing, there is no problem, there is no transient state here. Okay, now from 1 0 you will go to 0 1, you will go to 0 1, from 1 0 you will go to 0 1. But what will happen? You can notice they will not change simultaneously. For a small moment what will happen? First this q0 will change, first this q0 will change. Okay, you can notice first this q0 will change, then q1 will change. So you can notice first this q0 will change, and then q1 will change. Okay, so this is the idea. Okay, and then from here you can go to here because q0 can change. Okay, so I hope the idea is clear to everyone. So you can notice these two transient states we are getting. So in the gate exam they can ask you how many transient states we will get. So the answer is two transit states are possible. Okay, only two transit states are possible. Okay, so okay, anyway, one more thing you should observe. What is that? In this, okay, let's observe this again. In this you can notice that if you have more flip-flop, let's assume here you can notice. Okay, so because of this propagation delay you can notice this. Okay, just notice this area. Okay, because of this propagation delay, so I can say that, okay, in this asynchronous circuit, what will happen in this asynchronous circuit? This clock will change, this clock will affect q0. So this clock will control q0, and then this q0 will control q1. Okay, so first this clock will control q0, then this q0 will control q1. Okay, so here I can say that this time period actually I can say this clock time period. Okay, so this time period must be enough. This time period must be, okay, this time period must be greater than the uh, collective propagation delay of both the circuits, because you can notice here. Okay, you can notice this clock will affect control this q0, q0 will control q1. When the, okay, the change in clock means change in q0, and change in q0, okay, then change in q0 means change in q1. Okay, so here I can say that definitely this clock period, okay, this clock period, definitely this clock period must be greater than 2 tpd. Okay, so anyway, this point we will see again, but I hope all these points are clear to everyone. So what is a transient state and all these things, I hope these points are clear. Let's see this another example. Here we have 3t flip-flop. Okay, so we have here 3t flip-flop, and what we are doing, again you can notice this clock we are applying to this flip flop, and you can notice the output of this first flip flop is working as clock for the second flip flop, and the output of second flip flop is working as clock for the third flip flop. Okay, so let's assume that this is q0, let's assume this is q1, let's assume this is q2, let's assume this is lsb, and let's assume this is msb. Okay, now let's analyze this. Again the same point will happen, that okay, the frequency, if this clock has f hertz frequency, then definitely this q2 will have f by 4, f by 8. Okay, I can say this is f by 8 hertz frequency, because this q0 will have f by 2 hertz frequency, and this q1 will have f by 4 hertz frequency. So you can notice this circuit will divide the frequency by 8. I can say this output, this q2 will have frequency f by 8 hertz. So this circuit will divide the frequency by 8. So this is actually a divide by 8 counter, I can say. Okay, so this is your divide by 8 counter. Okay,